By late January, parts of the northern hemisphere are buried under feet of snow, locked in deep freezes with few hours of weak daylight. 6 months later, those exact same streets and shorelines are sweltering under a high, intense summer sun. Because Earth's orbit is an ellipse, rather than a perfect circle, the intuitive conclusion is that we experience summer when we fly closest to the sun, and winter when we drift further away into deep space. But the timing is entirely backward. Earth reaches its closest point to the sun, a position called perihelion, about 91.4 million miles away, in early January. We are at our closest point to the solar fire right when cities like Boston and London are freezing. 6 months later, in July, Earth reaches aphelion. We are roughly 3 million miles further away from the sun, right in the middle of the northern summer heat waves. Physical distance from the sun is a total illusion. It has practically zero effect on the temperatures we experience on the ground. The actual mechanic driving climate change is a simple tilt. Earth's axis leans exactly 23.5 degrees off a vertical line. As the planet completes its orbital lap, this axis exhibits parallelism. It remains stubbornly fixed, pointing toward the exact same spot in deep space. With the axis locked in place, this orbital lap forces the northern and southern hemispheres to take turns leaning directly into the sun's path. Looking at this orbital diagram, we can anchor ourselves on June 21st, the summer solstice. Here on the left side, the Earth sits in a position where the northern hemisphere is leaning directly toward the sun. The critical factor here is insolation, the amount of incoming solar radiation striking a specific area. A beam of light hitting a surface straight on concentrates all its heat into a tight, intense circle. But if that same beam strikes at a harsh angle, the exact same amount of energy gets stretched and diffused over a much wider, weaker area. Because the northern hemisphere leans inward during June, it catches those solar rays perpendicularly. It receives highly concentrated, direct hits of radiation, which drives up temperatures and stretches out daylight hours. At the exact same moment, the southern hemisphere is tilted away. It catches those same sunbeams at a slanted, glancing angle, diffusing the heat and dropping the region into winter. Summer is the geometric result of receiving highly concentrated solar radiation, completely independent of how close the planet actually is to the sun. 3 months later, on September 23rd, the Earth arrives at the autumnal equinox. Our position in orbit means the axis is now leaning sideways relative to the sun, neither toward nor away from it. During this neutral window, the sun aligns directly over the equator. For a brief moment, the entire planet receives an equal 12 hours of day and 12 hours of night. Now look at the right side of the diagram, marking December 22nd, the winter solstice. The axis itself hasn't moved, but our new position on the opposite side of the sun means the North Pole is now leaning completely away from the light. Sunlight reaching the northern latitudes is now striking at a severe angle. The solar energy spreads out thinly across the curved surface, causing the freezing temperatures and short, dark days of winter. A year, then, is a cycle of shifting sunlight angles, continuously sweeping back and forth across the planet's surface. There is a delay in this system. If June 21st delivers the most direct, concentrated sunlight to the north, we should expect it to be the hottest day of the year, yet July and August are consistently warmer. This gap is caused by thermal lag. Earth's massive oceans and vast land masses take weeks to fully absorb incoming solar heat and equally long to release it. The peak temperatures lag behind the peak sunlight. Land absorbs and releases heat much faster than water. As the continents rapidly bake in the summer sun, the hot air rises, creating massive low-pressure zones. These vacuums drag in cooler, heavily saturated air from over the oceans, forcing it inland. As this moist air hits the heated land masses and mountain ranges, it rises, cools, and triggers widespread rainfall. Entire populations rely on this seasonal wind reversal, the monsoon, for their fresh water and agriculture. The seasons act as a massive thermodynamic engine, driving the planet's entire water cycle and pushing atmospheric currents across the globe. Billions of years ago, a massive celestial body named Theia collided with a young, developing Earth. The impact blasted enough debris into orbit to form our moon and permanently knocked our planet off a straight vertical axis. This cosmic accident created an environment defined by constant, cyclical change. Biology had to adapt to surviving deep freezes and blistering heat, hardwiring entire species to undertake massive seasonal migrations. Human civilization is entirely bound to this rhythm. We time our crop cycles, manage our water reservoirs, and build our food supplies around the reliable return of these shifting angles. Without a random 23.5-degree collision early in planetary history, the global ecosystems and agricultural systems we depend on would never have developed. As Earth continuously loops the sun, it executes a brilliant, constant redistribution of solar energy from pole to pole. The next time you feel the first crisp chill of autumn or a wave of summer heat, you're experiencing our planet's slanted geometry moving through the solar system.